to get the maximum efficiency. What does it mean, efficiency first? Issue between the output of the system and the input. If you have a system and the system has input, whatever the input, and the output, let's say that the output is the output power and the input is input power, the efficiency of this system is equal to the output divided by the input. And if you wish, you can do it, multiply by 100, you get a percentage. That's the efficiency. What is the relationship between the input power and the output power in any system? Guys, you got out, you put 100 watt, you got 90 watt, right? What is the 10 watt? Loss, right? Losses. So we'll say that the P input is equal to the output plus P loss. Now we'll go specific. Single phase transformer. What are the losses in transformer? Two losses. What last time? One, it's called embedded in it hysteresis loss and the wind loss. So we'll say we have one cool, it's called cool loss, and we call it PC, cool loss. And what about the other one? Eddy and hysteresis, both they are included in cool loss. They are fixed, by the way. We consider fixed. If you are working with the specific frequency, it's fixed. Specific voltage, fixed, yes.
So the heat, is it?
It's lost because it produces heat, yes, when you put the heat, but without load. Once you put load, you add more loss because the current winding, and windings we said before, it's made of wire. And the wire has a resistance. So we have copper loss. So we got two losses. Cool loss, copper loss, and transformer. Cool loss, we believe it's fixed, almost fixed, constant. What does it mean? Does not depend on the load. Whatever load you are using, it's fixed. If it's 300 watt, 300 watt, doesn't matter. You have rated load, you have 50%, 75, doesn't matter, fixed. How can you calculate the cool loss? No load test, and I believe yesterday they didn't stop in the lab doing the both tests. Copper loss. So it's equal I squared times R. Working with the transformer without obtaining the equivalent circuit, I mean, you have primary side, you have secondary side. So you got to get the copper loss in each side. Like a primary side, say I1 squared times R1. And let me just write it down. So if you don't have equivalent circuit, you will say in the primary equivalent one, I1 squared times R1. What's R1? The resistance of the primary winding plus the loss on the secondary side. I2 squared times R2. What's R2? Is the resistance of the secondary winding. What about if you are working with equivalent circuit? It depends which side. If you are using the equivalent, so it depends which side. If you're referring all parameters and variables to the primary side, you're working side one. So you will have I1 squared times the equivalent resistance to refer to the primary side. That's enough, one term. If you are operating on the other side, so you'll have I2 squared time the equivalent resistance referred to the second side. This or that. That if you want to have maximum efficiency, and we already explained here what does it mean, the efficiency. Let me write it again. Efficiency, it's equal the output power divided by the input power. What's input power? Input power is equal to plus loss. What's the R loss? PC, which is the core loss plus copper loss. So you get the minimum loss. The minimum loss happens if the copper loss equal the core loss. Core loss does not change. It's fixed, like say 100 watt. Copper loss can be above 100, below 100, or 100, but the maximum efficient happen if both are equal. The variable is the copper loss. So it's in your hand. How you change the copper loss? By changing the current, the load itself. You choose the load in a way that the losses in the winding will be equal to the core loss. So we'll say that that will be maximum when copper loss equal core loss. That's what we said last time. Now let's go to the problem here. The transformer, the parameter are given are 1, R2, X1, X2. Not referred to any side, just everyone on its own side. And that's the rating value, 120 kilovolt amp, 2400 to 240 voltage. So that's the high voltage side, that's the low voltage side. And they said that to get the maximum efficiency of this transformer, the load should be 70% of the rated load. And the power factor is 0.8 lagging. So if you do that, you'll get the maximum efficiency. Let's just now go through the problem one by one. The first question is find the apparent power rating of the transformer at maximum efficiency. So you want to find the maximum, the rating value of the transformer at maximum efficiency. Okay. So first, to solve this problem, first we'll ask ourselves, if you want to find the rating value, what is the rating value? They said kVA. So do you want the apparent power of the transformer when it's max? First, how can you calculate apparent power? S. You multiply the voltage by the current. Which voltage, which current? Is it the voltage? If you want to calculate on the primary side, you multiply V1 I1. On the secondary side, V2 I2, because what would be equal? Actually, it's given here. It says anything on the plate of the transformer means the rating value. So I'll say the rating value, not the maximum. The rating value is equal 120 kilovolt amp. But they want it at the maximum efficiency. We get it. The voltage doesn't change, but the current will change. You change the current because the load changed, the current changed. So you pick the load to get the maximum efficiency. So the voltage, you can say that if you are going to work, let's now agree about something. We're going to work on the primary side. So everything referred to the high voltage side. That's the high voltage side, the primary. You can call it 1 if you like, and this 2. So everything will be referred to 1. So the rated load will be at 240 volts. So the secondary 240 voltage. So we'll say that at rated load, they are using the rated voltage. V2 is equal to 240. If you are going to refer to the primary, what you get, V2 dash is equal A V2. So we need to find the turns ratio. How you find the turns ratio? The turns ratio it's given here. When you see 2400, 240, that's the turns ratio. So let's do it. 2400 by 240, that will give you 10. So turns ratio A is equal to 10. So if you want to find V2 dash on the other side, so it will be 10 times 240 is equal to 400 voltage. Somebody say, okay, just why in big 2400 is given there? Why you do all this? Well, because not every time you operate the transformer at the rated voltage. I can tell you it's operating at 200 volts. So I don't want you to get just to get used, you break the other one up. No, maybe it's 200 voltage. So in this time, it will be 200 times 10 will be 2000. All right. How to find S? How to find S? I multiply this voltage by the current. So what do you need? You need I2 dash. How you find I2 dash? Go back here to the notes. They said that they are operating at 70% of rated load. So if you know the rated load current, you can get the current of the load that caused the maximum efficiency. How can you calculate the rated load? You divide S by V. Why? Because S is equal to V times I. So at rated load, the voltage is equal V2 and I is equal I2 rated. So this is call it, for example, R, the rated value. How can you find the value of the rated? But I'm working on the other side, so I will say V2 dash, I2 R dash, working on the primary side. S is given. The rated value of the apparent power is given here with the transformer, 120 kVA. So I say that's 120,000 volt ampere is equal to V2 dash. I got V2 dash, 2400 voltage times the current rated value. Let me make it F here. So I'll say means full load, rated load or full load. So from this equation, I can find the load current at full load case referred to the primary side. I2 dash full load is equal to S 120,000 divided by the voltage 2400, and you get 50. So that's the current at rated load referred to the other side. So if you want to picture that, if you have the transformer like that, and if you have you want to get the rated load, we don't care about the value of Z. So this is rated load, and the voltage was 240 voltage. The voltage here will be 2400, and the current here will be 50 amp. Have full load. Now I'll go for the maximum efficiency. So maximum efficiency happen at, we'll go back and just read it, 70% of the rated load. That will cause the maximum efficiency, 70%. So now I can find, let me sketch also another picture. Now, this is another load, which will give the maximum efficiency. It will be 0.7, 70%. So I will say the current I2 dash at maximum efficiency, let's just make it this efficiency thing, will be equal to 0.7 times the full load. So 0.7 times 50 amp, that will be equal 35 amp. So you can say that the current now is 35 amp. Not complete, it's only the magnitude was given the power factor. You cannot define the current only by you say that it's 70% of the rated value at 0.8 lagging power factor. So now I can write the current is equal 35 and lagging will be negative, the power factor 8, cosine minus 1.8. Then you can get the current as a phasor. What's cosine 0.8?
36.8699.
Say 37, almost. Yeah. Well, so that's the current that calls maximum efficiency. That's for the maximum efficiency. So maximum efficiency. Now I can find the parent power responsible for maximum efficiency. How we get this? As we said here, we multiply the voltage by the current. So we'll say V2 dash doesn't change, but now the current, instead of using I2 full load, I'm going to use I2 for maximum efficiency. Yes.
Isn't it negative?
Yes, it is. Yeah. Thank you. Now the voltage time the current that caused maximum efficiency, call it just S efficiency. So distinction between, and this one S, call it full load. So the voltage doesn't change. V2 dash is equal 2400 times the current for the maximum efficiency is equal 35. I'm calculating only the apparent power. I don't have to use the angle. So what we got 84,000. That's what the answer for the first one. So to get the maximum efficiency, the load should have apparent power equal to 84 kVA. Let's just see what the question here. Yeah. So we got the first one, the rating, kVA rating. Any question on this part? To know the power that's required to get the maximum efficiency. The second question is find the maximum efficiency. Find the maximum efficiency. And that's the definition of the efficiency. That's the definition of efficiency. Output power divided by input power. And input power is equal power output plus loss. So let's first think about it. The maximum. So to get this, you need the output power, you need the core loss, you need the copper loss, right? That's what you need. Let's first find the output power. Can you find the output power that causes maximum efficiency? How can you calculate the power of anything? You got to know the voltage, right? The current, the power factor. Three things. So the output power is equal V 2 dash I 2 dash cosine theta for the power factor. That's the same as power factor. But not any current. That's the or at any for any case you're going to do that. But if you want the full load power, what you'll do, I2 dash will be I2 dash for full load. If you want the output power when it's maximum efficiency, what current you're going to use? The current that caused maximum efficiency, which is I2 dash efficiency. Do you have everything? Yes, we do. Now you have the voltage, it's 2400 times I2 dash for efficiency, we just got it here, equal to 35. Take only the magnitude, 35. Times the cosine theta, power factor is equal 0.8. And you get the power. Because we said that we are doing all calculation referred to the primary side. Yes, if you are using the secondary, we'll say only V2, I2 cosine theta. But I'm doing everything on the primary side. If you want to do it on secondary, you can do it. That's okay. but all calculation should be on the second. So the power, calculate the power, is equal to 7200. That we need core loss, we need copper loss. Can you get core loss? I'll get. Can't say negative. Okay. But can you calculate the copper loss? Yes or no? What do you need to calculate the copper loss? Resistance, the equivalent resistance. If we're working in the primary side, so what do you need? You need R equivalent 1. Let me just sketch the. If you have everything on the primary side, so you have resistant, you have conductor, and you got the reflected load, and you got here V dash, V2 dash, I'm sorry, which is 2400 voltage. You know the current, I2 dash efficiency, which is equal to 35 and angle negative 37, 35 and angle negative 37 amp. That's I2 dash efficiency. But you need R equivalent to 1 and X equivalent to 1. True? Actually, when you want to calculate the copper loss, you don't need X. True? You need R only. That one that causes copper loss. So I need to find R equivalent to 1. R equivalent is equal R1 plus A squared R2. That's for the primary side, and that's for the secondary side, and A is the turns ratio. That's if you are referring to the primary. If you are referring to the secondary, if you want to work on the secondary, so R equivalent 2 is equal R2 plus R1 over A squared. Okay. It's given. Let's just get the information here. R1 is equal to 0.75 and R2 is equal to 0.01. Remember these two numbers. 0.75, 0.75 plus A squared. A is equal to 10 and R2 is equal to 0.01. All right. So we have 0.75. 100 times be 1. So it's equal 1.750. So that will be the total equivalent resistance on this side. Right, 1.750. So if the current I2 dash going through this winding on the primary side, it will cause copper loss. Now I can calculate the copper loss. Side 1, it's I2 dash square, not any I2 dash. The one that causes maximum efficiency times R equivalent 1. The current, you need only the magnitude. When you calculate the loss, magnitude square. The resistance would just calculate 1.75. And we get the copper loss. I did that, it's equal to 2143.75 watt. So that's the copper loss. So I'm almost there because I need to calculate the efficiency. I need output power, cool, loss. I got everything except variables. So in this case, you can say that at maximum efficiency, we know that. So the cool loss would be the same thing, 2143.75 watts. We have everything. Now we can calculate the maximum efficiency. So the maximum efficiency is equal to output power over input power. Input power is equal output power plus cool loss plus copper loss. The output power, we got it, 67200. And plus, those are equal. So just can multiply it by 2. And here you go, 2143.75. And then you can multiply by 100 to get it by percentage. This I found that's equal to 94%. Any question this part? We did A and B. We want the efficiency. We calculate what did we just calculate just right now? We calculate the maximum efficiency. The third one is the normal one. Calculate the efficiency at full load and 0.8 power factor. Like, you want to calculate the efficiency when it's not the maximum, when they have the full load. What would be? Every two work together in this practice and just calculate this one, efficiency at full load. And you have the all information here. Yes. Efficiency at full load. Full load. Slide. All information you need on this slide. I give you the formula here, so you don't have to flip your efficiency. Look at it. I give you the copper loss when it was at maximum efficiency, and you have the rest on the graph. So.
Coverage with this. But So I'm guessing the whole problem is
Let me see. Is up? Right. You do the problem, I gave you the formula already. The efficiency is correct all the time. Output power divided by input power. Input power is equal output power plus the loss. Always the losses, you got two losses, cool loss and copper loss in the transformer. Output power, copper loss change with the load because the current will change. So you're going to use the full load current, which is 50 amp that we did before. So the change will be like you multiplied 50 by 2400 times the same power factor 0.8, you get double power. The copper loss, I2 dash squared at full load 50 also 50 square time RE1 equivalent that we did last time. Cool loss, when I went through somebody or some student, they did cool loss equal copper loss. No, cool loss equal copper loss only at maximum efficiency. Fact number two, cool loss does not change, does not depend on current, does not depend on load. What does it mean? Once you calculate one time, use it in any load. Did we do it? Yes, that's why I give you here. Copper loss at maximum efficiency is the value. So, answer for the full load efficiency, it's 93.6%. That's the final answer. I will post the answer on the folio. 93. That's equal 93.6%. The last question, find the equivalent cool loss. Equivalent cool loss. What's equivalent cool loss resistant? What is that? What do you call it? Cool loss resistant. The parallel branch. That's the system of primary and secondary winding of the transformer. Equivalent reactance, both windings, primary and secondary. That's the parallel branch that you get it in the lab, no load test or open circuit test. That's RC1, the equivalent or cool loss resistant. XM, magnetizing reactance of the transformer. The question is find cool loss resistant, which is RC1. How we do it? How can we calculate RC1? Today in the lab. And RC, forget about what's the relation between power and resistance. Current square terms are, or question here, when you use I square R and when you use V square R. The voltage applied to the branch, which is in parallel, use of V square over R. If it's in series like the equivalent resistance R, example, what we did, said I square R. But for cool loss, it's parallel to the voltage. RC1 across V1. So and that represents the cool loss. So the power in this RC will be the cool loss equal E square 1 RC1. Now I want to find RC. So RC1 is equal V1 square over PC. What is the value of V1 square? V1? What is the value of V1? $2,400. Well, be careful. It's equivalent. It's equal to the rated value in this case. But as I told you, the transformer was 2400 240, and we used the rated value 240. What about if they told you are using 200 voltage? You have to be aware of that. If you have 200 on the secondary side, use the turns ratio, you will have 200 here. At no load. At no load, this current here, I2 dash, is equal 0 if you don't have load. Well, that will be open circuit. So the I1 will go there. Anyway, so if there is no drop across the impedance, so the voltage here, V2 dash, will be equal V1. So in this case, yes, V1 is equal V2 dash. That you did it, 2400. I know the same value, but I have to explain why. Because if any change happens, any problem. So V1 is equal to 2400. You put it here, 2400 square over the power, the cool loss. You did it. The cool loss, we said it's equal to 2143.75, and you get the resistance. The value of the cool loss resistance was equal to 2686.9 ohm.